Hi. Today we are going to be doing our lesson on Hess's Law and Calculations, which is part of the Unit 3 Chemistry in Society. Our learning intention for this lesson is to investigate Hess's Law through experimentation. Obviously we can't do a real experiment, so we're going to do a theoretical one, and learn how to perform associated Hess's Law calculations. We want to be able to state what is meant by Hess's Law, have an understanding of how Hess's Law can be proved, and we're going to do that by viewing the results of this experiment. We're also going to carry out Hess's Law calculations, hopefully successfully. So first of all, what actually is Hess's Law? Well, it's a relationship in physical chemistry named after Germain Hess. A lovely picture of him is up in the right-hand side corner. And he is a Switzerland-born Russian chemist and physician who published it in 1840. So the enthalpy change for a chemical reaction is independent of the route taken. That is Hess's Law. And what that means is it doesn't matter if you go from A to B, A to C to B, or A to stage D to stage E to B. All of the enthalpy changes should add up to the same number. So delta H1, which is the value for route 1, should equal delta H2 plus delta H3, which should also equal delta H4, delta H5 plus delta H6. So it doesn't matter which route to get from the start of the reaction to the end. If there are intermediate stages, that's fine. The enthalpy change should still be the same. So according to Hess's Law, like we just discussed, the total enthalpy change for routes 1, 2 and 3 will be identical. When we do this in the lab, obviously it's going to be an approximate value. It's not an absolutely identical value, but that's due to error that's built into experimentation. So what we're going to do is we're going to have a wee look at a Hess's Law experiment that we would normally carry out in class, but obviously you can't do that. So I'm going to try and talk you through and explain where we're getting the results from, and hopefully when we work through the calculation, you'll see that this is true in experiments. So here's our reaction here. We've got some potassium hydroxide going to potassium chloride. So that's route 1. Route 2, what we're going to do is dissolve the solid potassium hydroxide in some water first to make it aqueous, and then turn it into potassium chloride. So that's the difference between route 1, but route 2A is dissolving it in water, and then 2B. Hopefully, if this experiment works, which it normally does, to be fair, when we do it in class, that the route 1 value will be equal to route 2A plus route 2B. So here is the method. There are 3 stages to this experiment, as we said, route 1, route 2A and route 2B. And in each stage, the highest temperature recorded is measured. Obviously, this is an exothermic reaction where we are getting heat energy produced by the reaction. So it's the highest temperature measured that we're going with. And we're just carrying this out in a polystyrene cup with a thermometer in it, so it's nice and insulated. For experiment 1, we're adding 1.2 grams of potassium hydroxide straight into the acid. For stage 2A, what we're doing is dissolving the potassium hydroxide in water. And then 2B, we're adding that solution of potassium hydroxide to the hydrochloric acid. And in each stage, the highest temperature was recorded. So the results, obviously, that you get in class would be put highest temperature and initial temperature to get that temperature difference. I have just put in some random values that we can work through as an example today. So remember, we're measuring the temperature increase, which means heat energy is released, and that tells us that this reaction is exothermic. So for step 1 of the calculation, what we want to determine is what delta H1 is. So what is the enthalpy change for route 1? And how we do that is actually really straightforward. It is going back to our National 5 knowledge of the EHCm delta T equation. So our energy released is calculated by the specific heat capacity of water, which is 4.18, times the mass of the water or liquid, and then times by the temperature change. So we had 4.18 because we're working with water, 0.025 because we had 25 centimetres cubed, and then 20 degrees C was our temperature change. So that comes out as a value of 2.09 kilojoules with your little negative there because it is an exothermic reaction. So if we want to know what the enthalpy for that change is, we have to calculate if 1 mole of potassium hydroxide was dissolved, because it's the energy released per mole we're looking for. So if we had 1.2 grams of potassium hydroxide dissolved, and that gave us a energy released value of 2.09 kilojoules, then 56.1 grams, that is the equivalent of 1 mole of potassium hydroxide, is going to be 56.1 multiplied by 2.09 divided by 1.2, and that gives us a total value for root 1 of 97.71 kilojoules per mole. So that is the enthalpy change for the root 1 reaction. And again, negative value here because it is an exothermic reaction. So what we're going to do is we're going to repeat this exact process for delta H2A and delta H2B. And then we're going to add those two together and hopefully come up with something that is approximately the same value as delta H1. So again, we've got 4.18 multiplied by 0.025. This time our temperature difference was 12 degrees. So that gives us a value of negative 1.254 kilojoules. We used 1.2 grams of potassium hydroxide again, which we did in every single experiment. We again scale it up to 1 mole, so it's 56.1 grams, multiplied by the 1.254 divided by 1.2. And that comes out as negative 58.62 kilojoules per mole. So that's 2A. Part 2B. This time the temperature change was 7 degrees. So again, we have 4.18 times 0.025 multiplied by 7 gives us negative 0.73 kilojoules. If we scale our 1.2 grams that were used up to 1 mole again, we end up with negative 34.2 kilojoules per mole. So to prove Hess's law, we want to add up the root 2 reaction total. So what we had was negative 56.62, so we're going to add negative 34.2 to that. Our total, therefore, for root 2 and added together is 90.82 kilojoules per mole. The enthalpy change we calculated for root 1 was 97.71 kilojoules per mole. So even though they aren't exactly the same, since the enthalpy change for root 1 was approximately equal to the enthalpy change for root 2 in total, so that's 2A plus 2B, that means that Hess's law is real and can be confirmed. So no matter what the root taken, the enthalpy change is the same. So we will be asked to do some Hess's law calculations, and the way you are asked to do this is you will be asked to find the enthalpy change value for a reaction, and you have to use some combustion equations to do this. The combustion values can be found on page 10 of the data booklet, which is this column here in the table. So these are in kilojoules per mole. They are standard enthalpy of combustion equations. It doesn't matter what the question asks you for, you are always to use combustion equations, and you've always to use this column in the data booklet. There are standard enthalpy of formation values here. Ignore those. You are always going to use the combustion ones. And I'll give you a wee worked example of how to carry out these equations just now. So worked example 1, you'd be asked a question like, find the enthalpy change for the reaction. So you've got copper oxide plus carbon monoxide gives copper plus CO2. And as you can see here, our delta H value is unknown. That's what we are going to be asked to calculate. Now, it's been really nice here and saying, oh, here's the combustion equations that you can use. You are supposed to be able to write combustion equations yourself. This was not a strength that we found out in the prelim, A lot of people are struggling on how to write combustion equations. That's a Nat 5 outcome that we covered. If you need more practice in writing combustion equations, then you can definitely let me know. Hopefully, once you have practiced enough of these, it will bring your knowledge back and it'll be fine, hopefully. So here are our combustion equations. We've got copper oxide, which is here in the equation. Its combustion equation is going to be copper plus oxygen gives us copper oxide, and the carbon monoxide plus oxygen gives CO2. And the values here have just been taken straight from the data booklet, so you can look those up. How to solve these is we need to say to ourselves, this equation at the top here is our target equation. So what we need to do is we need to manipulate equations 1 and 2 to get them to match up with our target equation. So on the first equation, we are dealing with carbon monoxide, and we can see that the carbon monoxide is on the left of the arrow in both equations. We have the same number of moles of carbon monoxide. So what that means is that that one can stay as it is. We have our carbon monoxide sorted. Then we go to our other reactants. So we've got copper oxide here. Now, if we look at equation 2, our copper oxide is not on the side of the equation that we want. Therefore, what we're going to have to do is we're going to have to flip equation 2. So I'm just going to write at the side here, flip. So that means that what was originally on the left will be on the right and vice versa. Now, an important point to note about flipping equations is if the forward reaction, now we know this from equilibrium, is exothermic, if we flip that, that then becomes the reverse reaction, which is then going to be endothermic. So what that means is this negative 155 value that we have here, if you flip the equation, you have to change the sign to show that it's now an endothermic reaction. So you flip it, it becomes 155 as a positive number. Please remember that. If you don't remember to do that, it'll mess up your entire answer. With the equations flipped though, we should have both reactants on the side of the equation that we want. So all we do now that we have our equation, is we cancel out any other species that we don't need. So we've got our copper oxide where we want it. So tick those off. We have our carbon monoxide where we want it. And we also have our carbon dioxide on this side of the equation. Our copper is here and here. So that is the target equation matched. Now you will notice that we have some extras here. So we've got this oxygen and this oxygen. Now whatever you are left with at that point, when you get this far through the calculation, should cancel. So what I mean by that is this oxygen underneath is on the right hand side of this equation and it's on the left hand side of the other equation. When something appears on both sides of the equations, then that means we can cancel them out. Only if there are equal numbers here. There are examples where you might have 2 oxygens on the left and 1 on the right, and that would cancel down to 1, but I'll explain that nearer the time. Now this is a very strong indicator at this point of the reaction if you have done the calculation correctly. If you have gotten to this stage and all of your elements match the target equation, they're on the right sides of the equation, and you are left with elements that don't cancel with each other, then you have probably done a step wrong. And my advice would be to restart the entire question just on a completely new piece of paper. Don't look at any of your old working and see if you can problem solve your way out of it that way. It's very easy to get caught up in all of the different working outs for this question. So just try and keep it simple and tick things off as you go and try and keep it really neat. Another tip as well is whatever you are doing to these equations, so when I flipped that equation, I wrote flip next to it. please do that, because if you end up making a calculator error somewhere further down in the question, if you have correctly identified what you have to do to each equation to get there, you will get partial marks for that. So the last thing to do in this equation then, because we're asked to calculate what the change in enthalpy, is simply to add the enthalpy values together for both of these equations. So when we do that, we have negative 283 plus 155, and that gives us a total value of negative 128 kilojoules per mole. And that is the question done. So worked example number 2. Calculate the enthalpy of formation of methane using enthalpies of combustion of carbon, hydrogen and methane. So page 10 of the data booklet, like I said, gives us the values for the enthalpies of combustion, but for this question, we are not given balanced equations. We need to come up with them ourselves. Now that, like I said a wee second ago, is a National 5 outcome. So if you need practice at this, then now is your opportunity. Remember, the enthalpy of combustion is the energy released when 1 mole of a substance burns completely in oxygen. So all you have to do to write these combustion equations is take each substance in turn, react it with oxygen, and write the products on the other side. If you have carbon reacting with oxygen, you're going to get carbon dioxide produced. If you have hydrogen reacting with oxygen, you're going to get water produced. And if you have methane, then you're going to get, as a hydrocarbon, CO2 and H2O. All of that should be pretty familiar from Nat 5. Again, like I said, if it's not and you need more practice, then you need to see your teacher as soon as possible. So these are the equations as written. Obviously, you need to balance them to make sure that there are the same numbers of atoms on both sides of the equation. And then you find the delta H values from page 10 of the data booklet. You must get them from the combustion side of the table, not the formation side. So now that we've got these, we can then have a look at our target equation and start identifying what we need to do. So first of all then, let's just take each substance from the equation in turn and see what we need to do. We have a carbon here on the left and it's here on the left, so that can stay. We don't need to do anything to the first equation, that's fine the way it is. The second equation, you'll see that we have 2 hydrogens here and we only have 1. So what we need to do to equation 2 is multiply everything in it by 2. So that means we're going to have a big 2 in front of the H2. Our half of oxygen now becomes 1, and we have 2 H2O. Now, whatever you do to the equation, you must also do to your delta H value. So if we have negative 286, what we need to do is multiply this by 2. And if we do that in our calculator, it gives us negative 572. So we now have negative 572 as an enthalpy value for equation number 2. We've got 2H2 here and 2H2 here, so we're done with that. Now the last equation, we have our methane, on the left. We want our methane on the right. So what we're going to have to do is we're going to have to flip this. So what that does is that will make our delta H into a positive 891 rather than a negative. Because if the forward reaction is exothermic and we flip it, the reverse reaction is endothermic. So now we have this equation flipped. We have all of our reactants in the right places. The next step in the reaction then is, of course, to make sure everything is cancelled. Now this is where, when you're writing it out in your exam or on paper, you should rewrite your equations flipped so that you can cancel everything out. But I'm just going to do it just now with you kind of in my head, and if you've written it down, you can do it in your jotter. So we have 2 oxygens, these will be on the right hand side since we flipped this, and those will cancel out with 1, 2 oxygens. And we should also have a CO2. If we've got one on the right, we should have one on the left. We do. It's here because we flipped this, so we can cancel those out. And again, we have 2 water molecules here, which appear here, but remember that's flipped, so those are on the left. So our water molecules cancel out as well. And you can see how this becomes messy very quickly. But that leaves us with carbon, which is in our target equation, 2H2, which is in our target equation, and CH4 on the right hand side, which is part of our target equation. So all we have to do is add up the enthalpy values that we have changed. So we have negative 394 minus 572 plus 891. And that gives us a total of 75 kilojoules per mole. The more of these that you practice, you find that they get kind of easier to recognise exactly what to do. So like any calculation, the more practice you get, the easier it becomes. So here we have, I think, 5 questions that we're going to work through. These have been taken from the last kind of 4 or 5 years of the SQA papers, and there appears to be at least kind of one of these in each paper. So they do come up often, and it's very, very helpful if you understand exactly how to solve them. So let's start with the first one. Again, if you are using paper here, you're going to probably want to write out a lot more of the steps than I am going to, but we can check our working at the end. So, calcium hydroxide solution can be formed by adding calcium metal to excess water. Solid calcium hydroxide would form if the exact molar ratio of calcium to water is used. So we've got an equation for the reaction here, and it's asking us to calculate the enthalpy change in kilojoules per mole for the reaction above by using the data shown below. So we are given the equations here. We are also given the change in enthalpy values for each combustion equation, which is good. So all we have to do is, first of all, identify how we can match this to our target equation. So our calcium here is found at the bottom, exactly where it is, so we don't need to do anything to that. Our 2 H2Os we're going to need to get from here. Now, on the first equation, they are on the right-hand side, and there's also only one of them. So that means that we are going to have to not only multiply equation number 1 by 2, but also flip it as well. Now, sometimes there will be scenarios where you have to flip the equations and multiply them, and that's completely fine. You can do that. So if we multiply, remember, everything needs multiplied by 2, so halves become ones. We have 2H2O. So we've got this now, and if we flip our equation 1, we'll also have our 2H2Os on the right side, which would be the left. So negative 286, if we type that into our calculator, multiplied by 2 is going to be negative 572. Remember, we've flipped this into an endothermic reaction, so it's going to be positive 572. Now, let's just check that we have everything else on the right sides of the equation. So our calcium hydroxide is on the right side as well, and this is where some people might be a bit confused. I'm sure there are people saying, right, there's an H2 on the right hand side. How is that possible? Well, how that's possible is in this flipped equation, our 2 hydrogens are actually on the right hand side. So those 2 hydrogens, if I just write them here just for a second, they will cancel with this 1 hydrogen on the left to leave 1 H2 on the right hand side. So that is where that H2 comes from. So we've got that as well. Let's make sure our oxygens cancel. We have 1 oxygen in the flipped equation, which is on the right hand side, will cancel with this oxygen on the left. So all of our elements or compounds, molecules, substances, they are cancelling on both sides, which means that we have done the steps of this correctly. So the next stage is for us to add up our enthalpy values, which are going to be, I'll just write this out. So we have plus 572 minus 986, and that gives us negative 414, and remember your units are kilojoules per mole. Now, a good indicator on whether we've done these questions correctly or not is if we get a whole number out. In most of these questions, in all of these questions, the answers are whole numbers. If you get something that's quite not a nice number, like a long decimal, then chances are you've maybe mucked up somewhere in putting the numbers into your calculator, and you should just double check. Okay, let's move on to question number 2. I want you to try these on your own now, and then watch the video to self-mark them. We've gone through 3 together now, so I want you to try a few on your own. That's the only way you're going to get better at this. If you just copy down what I'm doing, then you're never going to learn how to do these by yourself. So make sure you are attempting them first and then watching the video for feedback. Okay, so exactly the same procedure. The only difference is this time we have 3 different equations. Now sometimes they can give you 3, sometimes they'll give you 2. It doesn't really matter because the process is exactly the same. So this question says, another reaction that produces sulfur dioxide gas involves combustion of carbon disulfide in the reaction shown. So we're given our target equation at the top, and we are asked to calculate the enthalpy change in kilojoules per mole for this reaction using the following information. So we have 3 combustion equations and 3 combustion values from the data booklet. So let's go ahead and have a wee look at our equation, see what needs done. So our carbon disulfide is on the left at the top, but it's on the right at the bottom. So that immediately tells us that we have to flip this bottom equation. So we're going to flip that and change the sides. So our CS2, if you want, this would be where you would rewrite this with the CS2 on the left, arrow carbon plus 2S. I'm just going to leave it where it is because I don't have an awful lot of room on the screen. If you're writing this down, I would suggest that that's what you do. So we want to flip that, and our carbon disulfide will then be in the correct place. We would like 3 oxygens. Now, I'm going to stay away from the oxygen just now because I'm looking at this and I'm thinking, well, there are 2 equations that have our oxygen in them. So if I multiply 1 by 3, I might end up with 4. So I'm going to move on to something else. The CO2 looks good where it is. It doesn't need to be changed or anything. And my SO2, the last one, needs to be multiplied by 2. So I'm going to multiply this by 2 and then revisit my oxygens. So we'll have 2 S's, 2 oxygens, and 2 sulfur dioxides. So now, as you can see, we actually have made our 3 oxygens on the left-hand side as well. So we've got our oxygen 2. So let's just multiply 296.8 by 2. We get negative 593.6. So that's going to be our new value. Our flipped equation is now going to be negative because it used to be positive. So we've got 87.9 kilojoules per mole. And at this point, this is where we can see if we can cancel out the species on both sides. So let me change to a different colour while we're doing that. So we should have 2 S's to cancel out on both sides, and we do. This is on the right hand side, this 2S is on the left. We should have a carbon solid on both sides to cancel out. Again, this is on the right, remember, because we flipped it, and this is on the left. These are our 3 oxygens. This is our CO2, our SO2, and our CS2 are all there. So that means that everything has cancelled out. So it's looking like we've done a good job in this so far. All we have to do is add the three values together. So we've got negative 393.5, negative 593.6, and negative 87.9. So if you total them up in your calculator, you should end up with negative 1075, and units, as always, are kilojoules per mole. Make sure you put those units in. They are in the question, so if you do not include the units, then that's fine. You won't be penalised for that. If you write the units and get them wrong, you will. So make sure when you're writing units that you absolutely know which units you are writing. So this Hess's Law question is a multiple choice question. It says, consider the reaction pathways shown below. According to Hess's law, the enthalpy change in kilojoules per mole for reaction X is, so reaction X is going from carbon solid plus oxygen to give carbon monoxide and half an oxygen molecule. So that is the direction that the reaction is going. We are told here that there is an intermediate step where CO2 is produced. So we have to calculate this route here, whatever this gives us, should in theory, going with Hess's law, be equal to X. So if we go here, we've got negative 394, and then this arrow needs to be reversed because we're going then to carbon monoxide plus oxygen. So if we reverse the kind of way this reaction is going, if it's exothermic, it's then going to become endothermic. So you follow the arrow down, so you have minus 394, and then to get up to carbon monoxide, we're going to have to plus 283. So if we do that in our calculator, negative 394 plus 283, we get negative 111, which is, in this case, answer B. Okay, second last one. So Hess's law can be used to calculate the enthalpy change for reactions that do not normally take place. So this is where doing enthalpy calculations are useful, because the formation of propine for its elements, maybe you can't calculate experimentally, so it's something that you can do theoretically instead, and that's why it's so useful. So you have 3 carbons plus 2 H2 gives us C3H4, and it says calculate the enthalpy change in kilojoules per mole for this reaction using the following information. So again, the question's been really nice to us and given us 3 combustion equations and also the associated enthalpy values. So we're just going to go ahead as usual and go through our target equation and see which equations we need to change. So our first substance in the equation is 3 carbon solid. So we're looking at the equations. The first equation has 1 carbon in it, so it's looking like we're going to need to multiply that whole equation by 3. So if we do that, we have 3 carbons, which we're looking for, 3 oxygens and 3 CO2. And then remember, we need to multiply our enthalpy value as well by 3, and that will give us negative, that'll equal negative 1,182 kilojoules per mole. Our second species, so that's our 3C done, is 2H2 again. Second equation here, we do have an H2, but it's only 1, so we're going to need to multiply the whole thing by 2, and that will give us negative 572. You'll realise that the same values come up all the time because they use the same combustion equations. And then to match it, we need to multiply everything by 2. So remember, halves become ones when you multiply things by 2. So now we've got our 2H2. Our propine on the other side, as we can see, we need to flip that equation at the bottom. So again, I'm going to go ahead and write flip on it. If I write those 3 things, so the times 3, the times 2 and the flip, and I get the end of my question wrong by typing something wrong into my calculator, I will get a mark just for writing those 3 things down. So it's very, very useful. This is where showing your working comes in really handy to pick up those concept marks. So if we flip this over, our C3H4 will then be on the right side. The only thing left to do is then cancel everything out and make sure that it cancels properly. So we have our water molecules on the right are going to cancel out with these water molecules on the left, so both of those are gone. Our 3CO2 on the left will cancel out with our 3CO2 on the right, so both of those are gone. And last thing is our 4 oxygens. Again, these are on the right hand side because this is flipped. So these oxygens, which totals 4, 3 plus 1, will all be cancelled out. So the only things that we have left in the reaction are things we are looking for, which are our 3C, our 2H2, and our propine is obviously on the other side of that reaction. So last but not least thing to do is to calculate the total enthalpy change. So we're going to have negative 1182, take away 572, and remember to plus your 1939 because we flipped that earlier on, and your total should come to 185 kilojoules per mole. And that's your answer. Last but not least, carbon tetrachlorides is prepared by the reaction of chlorine gas with methane, and it gives you that equation below. Calculate the enthalpy change in kilojoules per mole for this reaction using the following information. So again, we're being given 3 equations to use here and 3 different enthalpy change values for those equations. And we're just going to go along each of the substances in the equation and manipulate the equations to match. So first of all, we have methane on the left here. Methane appears on the right in this equation, so straight away we've got flip equation number 1. There is the same number of moles of methane, both of them are 1, so we're not having to multiply anything out in the first equation. All we're doing is changing the delta H from minus 75 to positive 75. We then have 4 Cl2s, and like I did earlier with the oxygen, I'm just going to leave that just now because 2 of my equations contain chlorines, so I want to see if any other numbers kind of balance them out first. Our CCl4 is in the correct place, which is here, so that's done. So is that. And then lastly, we've got 4 HCl's. So we only have 1 HCl at the bottom. That means we're going to need to multiply everything in that equation by 4. So this time, rather than the halves becoming 1s, if we multiply a half by 4, it's going to become a 2. So we're going to have 2H2, 2Cl2, and we're going to have 4 HCl. So now we have our 4 HCl, and if we look at the other side, we now have 2 plus 2 Cl2s, which is 4 Cl2. So these are part of the target equation as well. Everything else in the equation should even out. So we have our 2 hydrogens at the bottom are going to cancel with these hydrogens here, which are on the right hand side. So those cancel. Our carbons as well are on opposite sides of the equation. This one's on the left and this one at the top is on the right. And then we're left with our substances in our target equation. So again, a wee bit that I kind of missed out there was multiplying that negative 92 by 4 is negative 368 kilojoules per mole. It's easier if we do the multiplications at the same time. So whenever we multiply that by 4, you should change that immediately because you might forget. So what we need to do is we need to add 75, negative 98 and negative 368 together, and that comes to a total of negative 391 kilojoules per mole. Very well done if you're getting these right. These can be quite tricky to pick up in like the first time you do them because it's something completely new. We've never done calculations like this before where you have to manipulate things and multiply them by 2, etc. So really well done if you're getting these correct. Hopefully by the end of this you will be able to state what is meant by Hess's law. I've given you a definition for it. You do need to know that definition off by heart, so make sure you memorise that. I want you to be able to have an understanding of how Hess's law can be proved. So, kind of following the structure of that experiment, using your energy released calculations to calculate the energy released and then scaling it up to a mole to get the enthalpy change. We have already done lots of those calculations in Unit 2, so it's not something that you can forget because it does show up in lots of different areas of chemistry. And then to carry out Hess's law calculations successfully. Every single one of the Hess's law calculations in the written paper is laid out the way that those 4 questions that we just done were laid out. So as long as you memorise the steps and how to do it, or just work through it logically like we did in the video, then you will be absolutely fine with those. If you have any questions, as always, give one of your teachers a message on Google Classroom and we'll get back to you as soon as possible.